So it's my great honor to be invited to share some of my research and also give some tips for career development. First, let us look at my research on network control and its applications. So here's some background about myself. I think I don't need to spend time here because Han already gave a brief introduction here regarding my background. And the outline of today's presentation is, first I will spend some time to introduce what is a network system, and then I will summarize and present my previous research achievement within this context. And finally, I think I will skip the last part regarding the future research plan because I think the time is not allowed me to do that. And so what are network systems? So network systems are complex dynamical systems consisting of a simple system interacting through a communication medium. So if you think about it, its application has fundamentally changed the way we live. For example, like smart grid, and this is Amazon robotic warehouse, where you receive a package, it's actually coming from this center. And then the social networks, which we're all using, like Facebook, Twitter, and also the transportation system, especially with all the connected vehicle technologies. They are all examples of network systems. And in next few slides, I will use some engineering example to further motivate what are network systems. So we will revisit some of these engineering examples as we going along. So the first example actually comes from power system, which is distributed energy resources coordination. So in power system, especially the distribution system, so power system traditionally is where you have power generated and then transmitted through the transmission lines. And then after feeder is become the distribution system where it goes to the end users like us. And the distributed energy resources has been developed rapidly recently for increasing the reliability and the efficiency for such distribution systems. And it contains distributed generation, energy storage, as well as electric vehicles. And the development of this will help the current power system to transcend to the smart grid, and it also can defer the investment on the current infrastructure. In order to coordinate such distributed energy resources, proper coordination algorithm is needed. And the second example also comes from power systems. So in power system operation, this power balance condition is very critical. Namely, whatever you generate, it has to be consumed by the end user. If this power balance condition is not held, then the frequency will not be maintained as its nominal frequency, which is 60 Hertz in the States. For example, when the generation is insufficient to supply all the loads in the network, then efficient and effective load shedding algorithm need to be deployed in order to cut the system overload so that the system will not be collapsed. And the third example comes from the transportation system, which is vehicle platoon. I have been working on this area when I was a postdoc at KTH, and there are quite few professors here still working on this. So the idea of vehicle platoon is to group a bunch of vehicles so they can travel together at a constant speed while also maintaining a safe distance between them. And it has been widely recognized as a very promising solution for reduced fuel consumption, CO2 emission, increased safety, as well as it provides you more freedom, so you can enjoy, because normally it's only required the driver in the front leader vehicle, while the rest can be autonomous. So you can enjoy do something, reading a papers or chat with friends when you are sitting at the car or truck. So these are the first other examples about the network. When we consider the network systems, normally the graph theory tool become very useful. So here, I won't spend too much time except emphasize 2 points. So in the previous examples I provided, the node will represent physical entity. For example, it can present a truck or a car in the vehicle platoon problem, and can present a human being in the social network, and present distributed energy resources in the DER coordination. While the information flow or the communication or information exchange is actually represented by an edge. So if I am friend with you, so we can share some information regarding certain stuff. So there will be an edge interconnecting us. And also although this topic has been studied for a while, there are still many challenges. For example, like each node only receives information from its few neighbors. And also with this limited information, each node has to design its local control. And quite often there will be a global objective has to be achieved through through only this local information exchange. So all these challenges has also has put network system become a topic of growing interest, which also inspired two IEEE transitions, actually in different discipline areas. And my previous research in past few years has been focused on developing distributed control strategy or distributed control optimization strategies in general, while I also keep in mind to apply the developed strategies or methodologies to application domain areas, such as power systems, as well as transportation systems. So next, I will focus on summarize my previous research achievement within this context. So I will use 4 examples as my representative work. The first 2 examples are the more on application areas, application side, while the last 2 areas, one of them actually was done when I was a postdoc at KTH, but we finished work at PNI. So the first research highlight is about the DER coordination. As I mentioned before, the developer of DER will help us will help the current grid to transition to a better smart grid. So in order to reap these benefits, proper coordination algorithm need to be designed. And there are several ways to do it. So conventionally or traditionally, what they are doing right now is there is a central control center which gathered information and provide the control signal to the entire system. Well, this centralized approach have some problems, and I think here a lot of people are doing distributed in certain sense. So we all know the centralized approach have certain advantage or limitations, such as high communication cost and the communication pattern, and also the limited flexibility. And of course, it does not respect the privacy if you consider privacy as a concern. So alternatively, it is desired to develop a distributed approach where each DER only maintain a set of variables and exchange this information with its few neighbors. And to further see how we can formulate this as an optimization problem, so here I present a simplified version of this DER coordination, which is we only consider the coordination among distributed generators. So consider network. There are n distributed generators, and each of them will have a cost function denoted as CI/Xi, where Xi is the power generation. And the optimization problem here is we want to minimize the total cost, while keep in mind we have two physical constraints in power system. The first one is each power generation has its physical limitations regarding how much power it has to generate and what's the maximal power my power plant can generate. And the second one is the one I'm talking about regarding the power balance constraint. So all the power generated has to be consumed by the end user. So this optimization problem actually right now back maybe 20 years ago, we know that according to the eco-incremental cost tutorial, there is an analytical solution where this CI/Xi prime denoted as a derivative of your cost function. And this lambda star is actually what they call it as a optimal incremental cost. You can think this one as the optimal value for your dual variables. I will skip the detail how to drive it, but I think it's pretty trivial for us to understand this. So the whole question is how can you learn this lambda star in a distributed way? And recently, last 2 or 3 years, there has been several consensus-based algorithms which provide you the solution how to learn this lambda star in a distributed manner. But there are still challenging remains. This work requires that the communication network is fixed, and also they do not consider communication time delays. While these two challenges remains, and that what motivate our study. And in my previous work, so we proposed this algorithm. I will explain in a second. One, we call it ratio consensus and the gradient algorithm. So here, instead, we have each generator or each DG, distributed generator, maintains a set of variables, and these variables are updated either based on its own information or the information received from its neighbors. So actually, this term, xi minus di, is actually the gradient of the dual function. And this is, if without this term, this whole algorithm reduces to something called the ratio consensus algorithm. That's the reason we call it ratio consensus and the gradient algorithm. And we know that without this gradient term, all this lambda I is the estimation of the lambda star. So all this lambda I will converge to an initial average of variable V. But with this gradient term, we don't know where all this lambda will converge to. Of course, we want it to converge to lambda star, but the way we prove it is motivated by the result of Angelina Nedich from Illinois. So here we prove it in 2 steps. So the first step is, although all the lambda will not converge to the initial average of variable V, but it will keep tracking the running average pretty well. And then the second step is we show that the running average actually converges to the lambda star. Of course, we prove it under certain assumptions, which is very mild. So the first one is regarding the cost function. So we only assume that the cost function CI/Xi is strictly convex as well as continuously differentiable, which is very general compared to the commonly studied quadratic type of cost function in the literature. And the second one is we consider time-varying communication topology. This is more general compared to the fixed topologies considered in the literature. And regarding this time-varying or switching topology, we only assume that the graph is uniformly jointly strongly connected, in the sense that the graph can be disconnected at any point as long as the joint graph is connected over a period of time. I will explain this concept in next slides by a simple example. So here, if you look at all the graph, G1, G2, up to G4, all of them is disconnected at any time distance. But the joint graph is connected. So we see that this graph is uniformly, jointly, strongly connected. And under the previous mild assumptions, we have our first result, which is that we show that all the lambda I will converge to the optimal incremental cost, lambda star, while all this xi converge to the optimal generation. Not only that, moreover, we show that this algorithm is robust to the time delay as long as the time delay is bounded. That's the only requirement. And this result is currently under the review. And the second research highlight is regarding the load shading. So the load shading, I have already mentioned. For example, when the generation is insufficient to supply all the load in the power network, so we have to decide which load we can cut. And traditionally, it's the same. This was done by a centralized approach, where there is a single control center which provides the signal regarding the average system overload to all the loads in the area. And of course, this approach suffered several drawbacks, as mentioned before, like the communication cost and the disrespect of the privacy, which also motivated we need to develop the distributed approach to handle this problem. And in the literature, the distributed approach, there are several algorithms, and most of the algorithm, actually the key point is how to come up with an average system overload. Because once we know this information, the proper decision can be made based on a local priority table, so what kind of load can be cut. And so far, most of the algorithm is based on the classical consensus algorithm, where it converges asymptotically, and also it does not converge to the average when you have time delays. So these two challenges, we have tackled each of these two challenges in different works. So regarding the first challenge, we proposed some algorithm which converge in finite time rather than asymptotically. And the second challenge is we use something called the ratio consensus algorithm. As I mentioned before, this is we show that even when you have directed graph and with time delay, this algorithm will converge to the average system overload. So the difficulty regarding the direct graph or time delay is that if you run the classical consensus, you will converge to the weighted average rather than the average. But instead of running one iteration, run these two iterations together, and the ratio of them converge to the average system overload. And this work will be presented tomorrow by one of my colleagues in Dallas, which is PEI's T&D conference. And those two are the work, most of the work I have done after I leave the KTH. As you can see, it still somehow applied the distributed algorithm or distributed optimization, but to some problem. And we actually show that this problem actually works in the real world. I will talk about at the very end if time provided. And the next two research highlights are actually the work I mainly done at KTH or slightly after I leave KTH. So here, I don't think I need any further motivation regarding this, but I would like to emphasize my research contribute regarding this consensus field is that the previous work, the consensus, we all know what it's about. It's about a symbiotic agreement regarding certain variables, which depends on all the agents. And then the literature, it has been studied since from the nature observation, where the fireflies synchronization was observed, and also from the physics community. And most of the work do not consider the input situation, where if we think that all the physical device has the bounds on its actuation which can provide. So for example, you cannot accelerate your car as fast as you can. So input situation is actually important to be studied. This is what my main contribution regarding this field. And to start with, we consider a very simple dynamics, which is single integrator. And our goal is to design a distributed control law to achieve global synchronization for such a system. And the controller we design is based on the relative state. And we show that this distributed control law will achieve synchronization or global consensus, provided the epsilon is chosen properly. This is the first work I have done here with one former postdoc, Yang, now in Tsinghua University, and Demos and Kali. And later on, we extend in the same also more complicated dynamics, which is discrete time double integrator dynamics. As now, you see that we have not only relative state, relative position, but also relative velocity. And we show that if alpha and beta, which is the feedback gain parameter of your distributed controller, are chosen according to this condition, actually the whole system achieve global consensus. And the difficult part to prove this result is how to come up with a Lyapunov analysis. And here we provided a novel Lyapunov function. As you can see, not only the quadratic term, but also contain a cross term. It is this cross term rendered the stability analysis. So research highlight 3 is about input situation. While input situation is a special kind of general nonlinearity, in my previous research at KTH, we also consider the general nonlinear dynamics. So here, the agent dynamic will contain 2 parts. So the first part is something we call inherent agent dynamics, which is nonlinear. And the second part is actually the influence from your neighbors. Here, this influence from the neighbors coming from the switching graph. And these two together complicate the dynamic we consider. Because normally here you have either single integrator is 0 or you have linear dynamic. And here graph normally is fixed. So the combination of these two actually complicate the problem a lot. And regarding this type of network, we first provide a novel or new concept of synchronization, which is called global phi synchronization. So phi basically is a function of all the agents' state. And we say that the whole network achieve global phi synchronization if all these phi function converge to a same constant. And the question here is, what are the conditions for achieving global phi synchronization? To answer this question, we consider 2 different cases depending on inherent agent dynamics is expansive or non-expansive. So the non-expansiveness definition is formally defined here. Basically, you can think your inherent agent dynamics is stable with phi as the Lyapunov function, which is also convex. And regarding this one, we have the result shown here. So the global phase synchronization is achieved if the graph is uniformly jointly strongly connected. I have already said that that is very mild assumption regarding the connectivity of the network. And for the expensive case, we focus on the case where the inherent dynamics satisfy the global Lipschitz condition. And for this case, our result is that the graph itself is uniformly jointly strongly connected. Itself is not sufficient to guarantee the global synchronization. What we need is that this global Lipschitz constant has to be less than certain threshold depending on the network parameters. So basically, this condition is driven to ensure that the dynamics due to the unstable dynamics due to this global Lipschitz part has to be dominated by the convergent dynamics coming from your neighbors. And the research highlight 3 is all about the synchronization or consensus. Although synchronization is an important problem for network systems, in my previous research, we also consider other type of dynamical behavior regarding this networked system. And to present such a result, let me first recall some result regarding a single agent, so it's not network. Regarding the single agent for the continuous time double integrator, and we know that the feedback gain, if are choosing negatively, then this controller actually achieve the local stability for this closed loop system, where this sigma is also a standard situation function. And not only that, there is a fundamental property that the local stability always imply global stability. It means that if you have situation function here, all this controller also achieve global stability for the closed loop system. This is the classical result due to Bernstein back 1999. And in my PhD study, we were asking the same question, but for the discrete time double integrator. And it turns out the result is is different. So what we have is we have this whole region which rendering the local stability for the system can be divided into two subsets. In one subset, we also achieve global stability for the closed loop system. While in another subset, the system exhibit periodic behavior. In my postdoc work at KTH, we were able to extend such a result from single system to network system. And here, we say that, here our result basically says that if these feedback gain parameters are chosen properly, then this multi-agent system will exhibit periodic behaviors. And this work will be appeared soon, I think. So I think I will skip my research plan, except I will make some acknowledgement. So all the work I present today are joint work with many great researchers. It was my great fortune to collaborate with all of them. They are from different countries, different institutes, and also they all have different, such as power systems, control, communication, and optimization. So I enjoy collaboration with all of them. With this, I would like to conclude my presentation, and I will be more than happy to take any questions. Thank you.